Hi, everybody. This afternoon, I'm going to talk about my project this summer, which I was mentored by Lauren Fry and Yi Hong, and it was titled Hydrological Modeling over the Great Lakes Domain for Subseasonal to Annual Forecast of the Net Basin Supply. That's a mouthful. I'll get to what all that means right after I introduce myself briefly. Again, Chase Pheifer. I grew up in small town, South Dakota. I went to a small college in Northwest Iowa and am currently at the University of Minnesota Duluth getting my master's degree in mechanical engineering, hoping to finish up next spring. So where I'll be going today is I'll discuss Great Lakes water levels broadly, and then I'll relate net basin supply to water levels. I'll talk about my task this summer and how it relates to net basin supply and water levels and what methods and findings came from that. So here we have a plot of the Lake Michigan Huron monthly mean water levels over the last decade. Lake Michigan Huron put together because Lake Michigan and Lake Huron rise and fall together. They're hydrologically one. So we can see some variability from year to year over this whole decade. A particular note is this 10 plus year period where we had low water levels from 1999 to 2014 or so. This looks like this in Traverse City in January of 2008, really low levels and inaccessible boat dock there, and also results in headlines like this from the New York Times talking about how low lake levels cause ships to not be able to carry as much cargo, which takes a toll on the shipping industry. So back to this graphic of Lake Michigan Huron water levels. After the low level period, we see a quick rise in the next 7 years from 2013 to 2020. We have a 6-foot rise from a record low to the second highest month on record. And that late 2010s period coincided with high water levels across the Great Lakes, such as Lake Ontario in May 2017. We saw some really bad flooding leading to this inundated dock here. And headlines like this from the Associated Press talking about how this big storm caused a ton of damage in fall of 2019. And this we see when high water levels are about, it means that storm damage is exacerbated because water is closer to infrastructure. And also this from the Minneapolis Star Tribune, talking about how high water levels can also hurt shipping because it can mean increased outflows, meaning more work for ships to work against the current as they come up the lakes. So all of that to say, water level is important for coastal people who live on the coast and for shipping industry. So that's something we want to be able to forecast better in order that we can prepare for it, and also in order that we can regulate it where possible within our means. And so what my objective this summer, fitting under all of that, is identifying indicators, hydrometeorological indicators of net basin supply, in order that we can better predict the water level at a monthly to an annual scale by use of a data-driven model to predict the net basin supply. And so I did this through exploring relationships between net basin supply and hydrometeorological parameters, mostly through a linear correlation or a Pearson correlation coefficient. And I thought about what windows of opportunity are there for these different hydrometeorological parameters to be used to predict net basin supply, what times of years or what conditions during a year afford better prediction. So what is net basin supply? How does it relate to water level? Here we have an equation for change in water level or change in storage, depending on what units you're using. And this equals the inflow from an upstream lake minus outflow to a downstream lake, plus precipitation over the lake, plus runoff from the basin into the lake, minus evaporation on the lake. So these last three terms are what are commonly called net basin supply: precipitation, runoff, and evaporation. And they are a component of determining the change in water level in a month. So if we have precipitation and runoff and inflow that is greater than outflow and evaporation in a given month, we see a rise in water levels. So if we can better predict net basin supply, we can better predict water levels. There's also what's called residual net basin supply. So if we rearrange the Great Lakes water balance equation, where we had the change in water level on the left-hand side, and we move the inflow and the outflow to the left-hand side, we get residual net basin supply equal to component net basin supply, or just net basin supply, plus a small error for things like groundwater influxes. So this is good because it's difficult to measure precipitation and runoff and over lake evaporation. And that's because we have a large area that the Great Lakes domain covers. Each of these bar plots represent the percentage of the portion of each basin that is either land or water. So Lake Erie is around 22% of the surface area in the basin is water, up to Lake Superior is around 39% is water, the surface area in the basin. So that makes it difficult to measure overland precipitation, difficult to measure over lake precipitation and over lake evaporation. And also, this is a graphic showing the percentage of the streams in the Great Lakes Basin that are gauged. And so around 70% of the streams are gauged. So difficult to have high confidence in our measurements of the three components of net basin supply, but we have high confidence in our in the values historically of the components of residual net basin supply. So when looking at historical data, we often use residual net basin supply instead of just net basin supply in order to have that higher confidence level. So that residual net basin supply is what I used in my analysis to correlate to overland hydrometeorological parameters. Given the large area and the large area of the Great Lakes domain and the difficulty of getting good measurements across it, I had to turn to what's called a reanalysis data set, specifically this European reanalysis data set, ERA5. A reanalysis data set takes historic observations and a present day weather model and assimilates them and outputs a uniform in space and time data set with many different climate and meteorological parameters such as temperature. So the parameters I included in my study, specifically again looking at the overland portion of the Great Lakes Basin, trying to correlate them with residual net basin supply, were precipitation, evapotranspiration, snow water equivalent or snowpack, soil moisture content, wind speed, air temp, specific humidity, surface pressure, and solar and thermal radiation. So basically throwing a bunch of these parameters at the wall, seeing what sticks to correlate with residual net basin supply. This is just an example of precipitation over Lake Superior's basin in December 2022, the average daily precipitation. So what I did is each month in my period of record that I looked at, I calculated the aerial average over the specific basin that I was looking at using a weighted mask like this. And since we have residual net basin supply on a monthly time scale, the data is in a monthly time scale, that's what I use to correlate these hydrometeorological predictors to residual net basin supply. And so what I did was using the Pearson correlation coefficient and splitting up the year into different months, trying to find what are good predictors of residual net basin supply. That looks something like this. So on the x-axis is the April average snow water equivalent on the Lake Superior Basin, and on the y-axis is April plus May residual net basin supply, so an accumulation into a future month. And each dot on here represents 1 year. And so looking at the strength of the linear relationship between these, the correlation coefficient is 0.56. So in this study, that's a fairly strong correlation. And so that means that the effect of April snow water equivalent persists even into the next month for affecting the net basin supply. So we have an indication in April of what the residual net basin supply will be in May. Moving to this graphic, so you can think of this graphic as containing a summary of 144 of the previous graphic that I just showed. So each month here is a month of snow water equivalent correlated to with a future interval of accumulated residual net basin supply. And each bar represents the correlation coefficient for that specific month and future interval relationship. If we look at March and April, we see month 0, so that's March snow water equivalent correlated with March residual net basin supply, not a strong relationship. In April, snow water equivalent in April residual net basin supply, not a strong relationship. But if we go forward and we add up residual net basin supply in future months, we see the effect of the present month, March, or present month, April snow water equivalent affecting residual net basin supply out many months into the future, which is helpful for thinking about, can we use the present month snow water equivalent to give us an idea of what the residual net basin supply is out future months up to 11 months as shown here. So rather than show you a bunch more of those plots for all different hydrometeorological parameters and for each single of the 4 basins, I'll summarize the strongest correlations across the basin here. So for overland precipitation, we see strong correlations in each lake basin and throughout the whole year, and especially persistent correlations in April through July and September through December. This is not surprising because overland precipitation is a strong driver of runoff, supply of water to the lake, and overland precipitation also comes along with overlake precipitation. Overland specific humidity for Lake Erie and Ontario is actually strongly correlated with residual net basin supply in January and February. And my guess, especially for Ontario, is because Ontario has the lowest ice cover on average. High specific humidity means low evaporation because there's already a lot of water in the air. And so if there's lower evaporation, that means the net basin supply is higher. Snow water equivalent in Lake Superior in April is strong, February through April for Michigan Huron, and December for Ontario, and these relationships persist out 3+ months, depending on which lake and which month you're looking at. And shallow soil moisture content, so a measure of the amount of moisture in the soil. I used 7-centimeter soil moisture content, which is from the ERA5 data set. Generally follows the same correlation as overland precipitation, just slightly weaker correlation. But in January through March in Lake Superior's basin, not strong correlations, likely because the ground is frozen during that time of year. And then stronger correlations in April and May. This is due to melting of snow and heavy precipitation leading to very wet soils and a higher supply of water during that time period. And finally, overland solar radiation has strong negative correlations throughout the year in all lakes, and especially in May through July for Michigan, Huron, Erie, and Ontario. And it persists especially in May and June. And this is due, as noted in this research paper, likely because this is the time of year when there's the highest precipitation in the Great Lakes Basin, so a high supply of water, which means clouds, so a reduced amount of solar radiation. And then in February and March for Michigan, Huron, and Superior see strong negative correlations as well. And my guess for this is that high solar radiation can mean some melting of ice, or it can cause high winds, which means more of the lake is exposed, leading to higher evaporation rates. So given all of that, those 5 parameters that I mentioned seem to be the best indicators of residual net basin supply moving forward, possibly using them to train a machine learning model for predicting net basin supply. And again, that ultimately helps us predict water level. But beyond my time here, what I'd like to see more is analyzing effects of teleconnections on the correlations, which we heard a little bit about today. And just based on a preliminary analysis that I did, it seems the relationships do get stronger depending on what the teleconnection indices that year, such as a weak El Nino winter seems to have stronger correlations for snow water equivalent in the Lake Superior Basin. So I'd like to see that further outlined. And this research paper did a really nice job with the Lake Ontario flooding events in 2017, discussing the effects of teleconnections on water supply and flooding in Lake Ontario. Orthogonalization and partial or semi-partial correlation allow for removing the interrelationships between hydrometeorological variables so that you can, for example, it can remove relationship between precipitation and soil moisture content so that you can just get soil moisture contents relationship with residual net basin supply. I started trying to do this, but I'm a bad statistician, so I couldn't do a good job. So I hope somebody else can. And then looking at different tests for relationships, Granger causality seems to possibly be a good fit for this. It's commonly used in economics and meteorology to find what variables cause another on a time scale, or principal component analysis to find what variables are the chief cause of the variance in another variable, such as net basin supply. And I'd also like to see some of my results verified by looking at other reanalysis data sets. These are references from my presentation. I'd like again to thank Dr. Hong and Dr. Fry for taking a chance on a mechanical engineer from South Dakota to look at hydrology for a whole summer, and also thank many people at Blurl and Sigler who've written great papers on the topic, which allowed me to get some understanding of the topic this summer. It was a lot of fun reading those papers. So thank you. Any questions?
Thank you so much, Chase. Great job. Questions for Chase?
Just with the great talk. I love seeing all the data, all the correlations. It's really awesome. I'm assuming, looking at the liquid water equivalent snowpack and how it relates to net basin supply for each of the individual lakes, I saw it got later as it got northern, right? And that's, I'm assuming, because the snow doesn't melt, right? And so that's why, because I thought about that for a while. And so I guess my question was more of a verification is.
Yeah, like you see with April snow water equivalent doesn't really have a strong relationship to residual net basin supply in the Lake Superior Basin, but if you have a lot of snow on the ground in April, it's probably going to melt in May, and so that's when that snow on the ground in April is going to affect the supply to Lake Superior. And yes, April for the upper Lake Superior, but December for Ontario actually. So.
Thank you.
Mm-hmm.
So when you were showing the correlations, it looked like they were all over land variables. And maybe I just missed it earlier on, so sorry if I wasn't paying close enough attention. But was that just because that's where the data was available? Like when you mentioned overland specific humidity, I would have thought over lake specific humidity would also be a factor, but maybe you just didn't have data for that.
No, there is data for that, but my objective this summer, at least what I went with it, was looking at overland portion of the basin specifically. So it is possible to look at the overlake data as well. I just didn't do that.
Sure. Yep. I'm sure there's probably a lot more certainty in the overland anyways.
So yeah, probably a good much approach. Better observations. Mm-hmm.
Any other questions for Chase? Okay, great job. Thank you so much.
Thank you.